Good afternoon, students. Good afternoon, students. So in today's class, we are going to see the experiment number 7, that is how to generate different waveforms using a delay program, right? So we are going to discuss two programs today. One is using the delay, right, and second is using again a delay, but both the methods of generating delay are different here. So in the first program we are going to generate a delay using no operation instruction, that is NOP, and in second program we are going to generate the delay using timers. Okay, so let us begin with this video lecturer of microcontroller, right? So we will discuss writing a program to generate a delay, right? So welcome to this video lecture. I am Professor Shivanand B. Channi, Department of ENC, Jain College of Engineering, Belagavi, right? So moving to the next slide, first we will see, as usual, we will see first the algorithm, right? So we will see the algorithm first, then we will see how to calculate, because this delay generation requires some calculations, right? Then we are going to see the program and the result. Okay, so coming to the algorithm part of this delay generation, here we are, instead of calling it as delay generation, we are calling it as writing a program to generate a square wave, right? A square wave, this will look like this, right? So initially its value is either 0 or 1, right? So if it is 0, then your square wave will look like this, and if initially it has a value equal to 1, and the square wave will look like this, right? So same repeated waveform, right? So what is happening here, if initially it is 0, right, it should remain 0 for certain amount of time to get this low level, right? To get this low level, then we are going to complement the value of this 0. After complementing, we will get 1, right? So it will make a transition from 0 to 1, right? So at this duration, at this time, then it is going to stay high for again a certain time, right? So in this manner, so same operation is going to be repeated to get a square wave, right? So if it is initially, if its value is equal to 1, again we are going to call a delay, right? And it is going to remain high for a certain time, and after that it will become 0, and it will remain 0 for certain time again, then it will become what, 1, right? So for complementing the values, we are going to use an instruction CPL stands for complement. So here we are going to use one pin of any port to generate this square waveform. Let us see which pin and what are the details, right? So first let us see the algorithm to generate a square wave on pin P1.0. So we are going to generate a square wave on pin number 1.0, that is 0th bit of port 1. So looking at the aim of that experiment, write an ALP to generate a square wave of 100 kilohertz frequency on P1.0, right? So finally we are going to generate a square wave, and if we measure the frequency of that square wave, that should be equal to 100 kilohertz, right? So first we will see the algorithm how to generate that using a P1.0. Here I am using P1.0, but you can use any one pin of any of the 4 ports, right? The first step to generate a square wave, we will use any one pin of any of the 4 ports. You can make use of any one of the port and one pin of that particular port. Then here we are using bit 0 of port 1, right? P1.0 means 0th bit of port 1, that is P1.0. Initially, when the microcontroller is reset or it is turned on, all the ports are configured as input ports. Input ports means the value written on those ports will be is equal to 1, right? Initially, when all ports are configured as input port, and if they are configured as input port means the value written to those ports is equal to 1. That means initially square wave will give 1, right? If we do not change this value initially before, right? So if I keep this value as it is, then initially the square wave will be having a t on period, then after that we will get a t off period, and the same t on and t off is going to be repeated, right? Then let the initial value of p 1.0 is 1, right? 1, because all are configured as input port, that means the value is equal to 1. To get the square wave, we need to complement the value of p 1.0, right? So initially it was 1. To get 0, we need to complement this 1. If I complement 1, we will get a 0, right? So we need to complement the value of p 1.0 to make it 0, right? So here we will use NOP instruction to generate a delay. NOP instruction, NOP stands for no operation, N stands for no, and OP stands for operation. So here the delay are generated using a NOP operation, because the delay is very less here. Delay is very less. As the delay goes on increases, we cannot use the NOP instruction, because NOP takes only one machine cycle, right? So instead of using NOP, we may use a nested for loops, or we may also use the timers to generate the larger delays. So in case of a lesser time delay, then we can go for a NOP operation. Then repeat the steps 4 and 5. 4 is complement and again generate a delay, introduce a delay, right? So these steps are repeated to generate the square wave repeatedly. Okay, so I hope the algorithm is clear to you, right? So moving to the next slide. Next we will see some calculations, because to generate a delay we need some calculations, right? Because the given frequency is 100 hertz, 100 kilohertz, right? So the frequency is given, right? So what I need to generate a time. Time is 1 upon frequency, which is equal to 1 upon 100 kilohertz, which is equal to, what is 1 upon 100 kilohertz? It is 0.001 millisecond, or you can also call it as 10 microsecond, right? So 0.001 millisecond can also be written as 10 microsecond, right? So let us see how to get that, what value or how many machine cycles you need, and how to calculate that delay, right? So we know that, let us assume the microcontroller is working with the crystal frequency of 12 megahertz, right? Actually 8051 or 89C51, what we are discussed in theory, that was working in 11.0592 megahertz, right? So let us take the integer value for this frequency, right? So let us assume that it is working at 12 megahertz, right? So even you can follow the same procedure to calculate the delay for 11.0592 megahertz. That is the actual frequency of 89C51, right? But we are not using that. We are using 12 megahertz to simply, it is an assumption to assume the frequency is equal to an integer value, right? So let us assume it is working at 12 megahertz, right? So we know that. So if you have not remember how to calculate this, or how to proceed with this calculation, so please go through. I recommend you to go through the delay calculation part of theory, right? So there I have discussed how to calculate the delay, and how to initially what all calculations I need to do before I go for actual delay calculations, right? So initially the the delay generation circuit, or the internal circuit of 8051 microcontroller divides this crystal frequency by 12, right? So it gets divided by 12. So what we will get, internal frequency is 12 megahertz. It will be divided, initially it will be divided by 12. So what we will get is 1 megahertz, right? So if I take its reciprocal, the given frequency of the square wave is to be generated, that is F given is equal to 100 kilohertz, right? So the given frequency is 100 kilohertz. Hence the time period of the square wave is 1 upon 100 kilohertz, which is equal to 10 microsecond. So this implies that. So this is what capital T is, the time period of one cycle, right? So if I start from 0, or let us I'll start from 1 only, right? So this is 1, this is 0, right? So if I take one clock frequency here, what one clock frequency or one cycle includes one T off, sorry, this is T on, this is T on, and this is T off, right? So one clock cycle includes one T on and one T off, right? So if I measure, and we know that this total time for one cycle is equal to, this total time is equal to 10 microsecond, right? So now if I calculate what is T on, what is T off, let us assume it's a square wave, that means T on is equal to T off, right? So T on is equal to, or T off is also equal to 5 microsecond. Just divide 10 microsecond by 2, then we will get the period or the time for T on as well as for T off, right? So this implies that T is equal to 5 microsecond. That means we need to write a program to generate a delay of 5 microsecond, right? But here it is given that F is equal to what we got from the internal circuitry, that is after dividing by 12, the given frequency, if it is divided by 12, we will get 1 megahertz, right? So we will get T is equal to, capital T is equal to 1 upon 1 megahertz, that is reciprocal of 1 megahertz is equal to 1 microsecond. That means internally the controller is generating a period of a time of 1 microsecond, right? So to generate a 5 microsecond, what we need, we need 5 such cycles, right? So to generate a 5 such cycle, to 5 such cycles, we need to multiply it by 5. That means the code, whatever code we write, that should encounter total 5 machine cycles. Hence it is required to build a program module that generates a delay of 5 microsecond. This can be achieved by inserting 2 NOP instructions in the loop used in previous program, right? So that we will see the program, we have not seen the program, right? It is there in the next slide. So this introduces additional 2 microsecond, so that we have 3 plus 2, which is equal to 5 microsecond delay generated by the module. Such a program is shown, not above, it is below, it is down, right? So I hope the calculation is clear to you people. So next we will move to the next slide, in which the program is discussed, right? So the program is very simple. So initially we will assume that all port pins are configured as input. That means the values written on those ports is equal to 1,